Hello, this is Saim from the University of Southern California. Today I'm going to talk about a 3D surface coil with deep learning based noise reduction for parotid gland imaging. We have a very diverse team in this project from United Kingdom and United States. We also have a startup company to manufacture our coils. I have no financial interest to declare. Imaging of facial region is quite challenging. It's because of the coverage of head coils, plus the susceptibility artifacts, and also the motion of the face. And 7 Tesla offers high signal-to-noise ratio, but imaging of facial region is quite challenging due to B1 shading as well, even for PTX. Yet, it's crucial because some of the neoplasms occur in the locations which are very close to facial nerve and also the parotid gland. 7 Tesla MRI has the potential to identify these regions, but unfortunately shading prevents that one. Here, the best idea is to use a surface coil since the parotid gland is quite closer to the skin. However, the current surface coils may not offer enough coverage and enough signal-to-noise ratio improvement for different regions and different depths. Here, we explore this idea, which is the 3D surface coil, to understand if we can offer any signal-to-noise ratio improvement and also increase the penetration depth. What we are doing is we are using this current surface coil, which is a transmit-receive surface coil, a traditional one, and we have another Y coil which is perpendicular to the X coil, and the purpose of this coil is to increase the penetration depth. The last but not the least is the sniffer coil, which is also a receive-only coil, and the purpose of this coil is to measure the noise in the environment and cancel it by using proper operations. This coil was manufactured in United Kingdom at MRI Coil Tech Limited. We also developed a 2D CNN architecture. We trained this architecture by using phantom MRIs and tested them on in vivo images. Before we switch to experiments, we run simulations on Sim4Life to analyze the shape of and size of the coil, plus the potential signal combination methods to improve the penetration depth. We also ran safety simulations on Sim4Life as well by using different realistic body models, and in our phantom experiments by using MRF thermometry, we have seen that the SAR results that we obtain, which is 3.8 watts per kilogram per 1 watts of electrical power, is quite in agreement with the simulation results. We then scanned participants, volunteers, and analyzed the effect of different channel combination methods such as sum of squares, adaptive combination, or the complex combinations as well. We have seen that based on the depth, different signal combination method may offer up to 10 to 30% of SNR improvement compared to a single channel only case. And we have observed that these penetration depths can be as high as 5 centimeters. Then we trained the network and tested it, and as you can see, for a single channel situation we have a signal to noise ratio of slightly below 900. However, when we trained the network and tested it on in vivo, we have seen that the signal to noise ratios can be increased to over 2000. You can see the results for different. Here are a few more slice examples. As you can see, the penetration depth of the coil is quite increased, and also as you can see below, the outside of region of interest is quite shady, where the internal parts are quite visible at a depth. During our experiments, we have seen that we can even image the cochlea. Although it wasn't in our region of interest or in our focus, we have realized that the cochlea in the middle ear canal can be imaged as well. Here is a quick demonstration for the imaging of cochlea, semicircular canals, and also the initial part of the facial nerve stemming from the skull base. And thank you very much for your time and attention. For more information, you can visit me at 2110, poster number 2110. Thank you.